Well, good afternoon, everybody, and welcome to this webinar called Wai Kahua Waka Footbridge. It's integrating culture, architecture, and structure. We really appreciate everyone giving up your time to join us today. Steel Construction would also like to thank NZIA for the opportunity to present to you all today. For those that don't know me, my name is Darren O'Reilly. I'm the General Manager of Steel Construction New Zealand, and I'll be facilitating today's webinar. SNZ, in a simple sort of description, we're like the master builders, but we're for the structural steel industry. And we've got over 800 company members, which range from steel fabricators, steel distributors, steel detailers, engineers, students, suppliers, right across the structural steel industry. So it's my absolute pleasure today to be able to introduce some great speakers on a great project, which the bridge was in our awards this year. It was a category winner, so and it's absolutely just a pleasure to look at. So our speakers today, we have Dan Crocker from DC Structures. He's the Chief Bridge Architect and Engineer for DC Structures Studio. He's a highly experienced bridge engineer. Dan loves bridges. With more than 20 years experience delivering projects across New Zealand, Australia, Pacific Islands, Central America, and Europe. After 12 years working internationally, he founded DC Structures Studios in 2016 to focus on pedestrian and cycle bridges. Dan is a chartered structural and bridge engineer, a chartered civil engineer, and holds a master's degree in architectural engineering. He's very passionate about creating vibrant, economical bridges that New Zealand communities can take pride in, supporting healthier, happier, and more connected places to live. Our other speaker is Dave Bellini. David is a structural project manager at Eastbridge, a Napier-based firm specialising in supply and fabrication of steel bridges, towers, and heavy steel infrastructure. Dan brings extensive experience in engineering project management, along with strong understanding of fabrication processes and steel construction. David's practical, detail-focused approach and deep knowledge of manufacturing enable him to translate complex designs into efficient building solutions. So before I hand you over to two fantastic speakers, I would like just to say if there's any questions, just please log them on the Q&A icon at the top of the screen. And if we have time at the end, we'll just go through some of those questions. I apologise in advance if we can't get through them all, but over to you, Dan.
Kia ora, everyone. My microphone working? Everyone can hear me? Okay, so the Waka Footbridge. I mean, as this image shows you, this is a pretty special, very bespoke bridge. Hang on. There we go. So we're going to keep the content. I mean, there's lots we can talk about on this bridge, but we're going to try and keep the content focused on some of the areas where architecture, culture, structural engineering, and fabrication overlap. And I think this is where some of the biggest value came from this bridge. So I'm going to give you a brief introduction about the bridge. You know, why is it there? What is it for? Then we'll look at the hull design for the Waka. And then we'll do a deep dive on some of the laser artwork and how that was accomplished and some of the challenges, some of the lessons learned so that you can use it in your own projects to advance what you're doing. And then we're going to focus on the fabrication and erection, which is a kind of behind the scenes, pulling the curtain back to see how these bridges are actually built, fabricated and assembled. So the introduction. So the location, this is in Gisborne. So you can see on the top left image where Gisborne is. You're probably all familiar with that. Now, in terms of the bridge location, we're around the corner towards the port environment. So in this main image here, you can see there's an existing landscape works, which is the Captain Cook Monument. And there's also this beautiful whale tail landscape works that's in itself award-winning. Now, historically, that area has been a very good place for visiting, but it's been kind of divided by the road. And this is quite a busy port road with lots of logging trucks and whatnot. On the far side here, this is an open area dock region where people can explore and really kind of enjoy the outdoors. So the main purpose of this from a functional point of view was to connect those two areas of interest so that you can walk from one to the other and create more of an active day experience. The client for this was Gisborne District Council. The iwi was Nati Onioni. The bridge designer was ourselves, DC Structures Studio. Constructor was Curry's Construction, and steel fabrication was Eastbridge. Geotech was Riley Consultants, and we had independent peer review on the structural stuff by Hofcon. So in general, it's the bridge location is Pahui Kai Iti Cook Landing, which is, we like to call it the whale tail area. It's a beautiful landscape works right by the Captain Cook Monument. The project forms part of the Gisborne District Council's Navigation Tarafiti project, and it's a harbour frontage, so partially coastal marine. So that affected some of the corrosion considerations. As you can see, it's a very striking form. One of the things we did very early on is engage with iwi and ask what kind of bridge they wanted. And they were very clear. They said the bridge needs to look like a waka. We don't want it to be symbolic of a waka. We don't want it to imply a waka. It needs to look and feel like a waka. Okay, so it was quite nice to get that very direct feedback. And I think they'd obviously had previous concepts that picked up some key themes of the waka, but played with it too much, and it wasn't quite what they wanted. They wanted something very literal. As the architecture and structural team, we were very keen very early on that the best way to give integrity to that cultural identity would make sure that the waka itself becomes structural. We were very clear day one, we would not create a traditional bridge and clad it to look like a waka. This bridge is fully structural. You'll see in some of the later slides, behaves like a traditional boat building form. Everything you see there, although it's the architectural outcome, is also the structural form. And we believe it's that kind of marriage of structure and architecture that's really added to the integrity of the final outcome. There are obviously also some really cool elements to this as well, like the piers were carefully thought out, and we've got the spiral staircases. But ultimately, it was that decision to keep everything structural and architectural as woven together as possible. The structure is a single span box girder with cantilever ends. And those ends are the prow and the stern, and they're continuous over the piers. Here we have the elevation. So a bit of lingo here. So we've got the tau ihu, which is the prow or the prow board, and the tau rapa, which is the stern post. So key elements of a waka. And obviously we have the hull. One of the key things we had to achieve was quite a high clearance over the port road because we get a lot of logging trucks. It's crazy, actually. We've got a lot of photos of this bridge. In almost every photo, there's a logging truck popping in and out. It's a very heavily used road, so we needed overhead. That led to some interesting kind of footprint issues of trying to get down. Now, in an ideal scenario, we would have had accessible ramps all the way down to the landscape. But those accessible ramps take quite a large footprint, and there just was no availability for footprint here. So for disabled access, they can actually get up on the dock side and come across to enjoy the views, but obviously they can't use the spiral staircase. But that's just a reflection on the tight footprint of this site. And even then we had to go for the spiral staircase just to really maximize what we can do with that tight footprint. From a pure engineering point of view, we've got pad footings founded directly on rock on the prow side, and on the stern side, we've got driven H-piles to rock. So a pretty straightforward elevation. Here's one of our favorite views. So in simple terms, this is a 36-meter long bridge. It's funny, it's difficult to measure the length because it tapers so much, but it is about 36 meters and the main span's 24. We've got a 2-meter usable width. So that's the width between the balustrades. It has a curved box girder main span, spiral staircase, and then we've got this just in the foreground here, this northern approach ramp that links us back to existing ground and those dock pathways. So the waka hull design. So I want to focus on this because this is one of the core elements of this design, is that integration of the architectural intent with the structure, with the fabrication. So we're going to focus a little bit on the hull. So like I say, early on, we decided we weren't going to clad a steel eye girder to look like a waka. We felt that that was creating almost a theme park ride from something that had very high structural significance. So we wanted to maintain the integrity of the intent with the integrity of the design approach. So you can see here on the left, this is how a traditional kayak, canoe, waka might be built. Now, a lot of waka are actually bored out from solid wood. Now, we couldn't obviously do that with steel. So this was the next thing, was saying, well, how would we normally build a boat? And you traditionally have ring beams and these longitudinal stiffeners, and then the hull is put over the top of that. And that's how the whole system works. So we've kind of mirrored that in how this structure works. So you can see here in the lower image, you have these ring beams with the shape to mirror what a waka hull would do. Then you have the longitudinal elements and also through the deck as well. And then the whole thing is clad with a steel skin. So as you can see, this is very similar to how you would actually build a boat if it were in steel. And as discussed before, the hull is the primary load-bearing mechanism. Here's an advanced or a zoomed-in view of that cross-section. So you can see here we've got a 10mm deck plate, and that has longitudinal stiffeners, and it's a 10mm to the hull, and again, stiffeners where we require them. And then we've got these ring beams. Now, the ring beams are spaced at 2.4 centers. And we also take that kind of pattern up further so that the hull kind of extends past the deck and becomes the balustrade. So you're walking inside what is effectively a boat-like construction method. Obviously, we had to work, we had a iwi artist, Nick Tupera, involved to represent iwi interests. And we were very keen early on to make sure that once we'd got to a point where we thought we had it right, send it to Nick, and Nick helped us tune that hull shape to make sure it was consistent with waka. So you can see here, here's one of the things we had come back. So originally we had it modeled. We thought, oh, that looks like a great waka. But it wasn't until Nick kind of put some lines over the top that we realized how much he tuned that kind of prow and stern areas particularly. So you can see it was quite a flat nose and stern, whereas now we've kind of lengthened that tapering. It adds a lot more elegance. We obviously elongated and curved the stern board, and the prow became much more kind of higher in technical complexity, but you know that's part of the outcome. So working and throwing ideas back and forth with the iwi artist was really important to make sure we maintained iwi buy-in to the final outcome. Here's some of the gnarly stuff. So box girders traditionally have a top and bottom plate, which is the flange. Now, where we're trying to curve to a point, that is not a traditional box girder form. So it's important for us to be able to model that. So this is an FEA, so finite element model of how that actually behaves. This was really important for us because this enabled us to actually deliver on our promise of a structural waka that mirrored the waka form. What we didn't want to do is dilute the waka form to fit with a kind of consistent box girder form. We wanted to make sure that we could take the box girder and match it to the waka. So it was the architectural intent and the cultural identity that drove the analysis, not the other way around. Here's just an example of that thing in action. So here we're running, this is probably live loads on the deck, and it just shows us the kind of magnitude of stresses we get. And this in turn enables us to identify where and where we do not need stiffeners. This is quite an interesting approach, really cool, quite technical. We also did a dedicated one for the prow and stern areas. We had to do quite a big focus on the body constraints of how everything fits together so it behaves as it would behave. One of the key things with the prow and stern is we have a PFC, so a parallel flange channel running all the way around these kind of board elements to give it stiffness and support. And you'll see that in some of the later slides, how that's quite important for the actual the detailing. But you can see some pretty sophisticated models, and this isn't actually the sophisticated version. I've printed this out at the 200 by 200 because it's the only one that can show you the squares. When we go down to the finer meshes, it's just a myriad of just points. So we ran numerous different versions to kind of understand the sensitivity of some of the assumptions we make, but quite fundamental to the outcome. Everything is focused on making sure the waka and its kind of architectural and cultural intent drive the structural. And it also comes on later, and you'll see in the fabrication as well. Right, yeah. So the FEA approach, not only did it allow us to do something quite innovative and make sure we got the form we wanted, it allowed us to be very tuned on materials. So we originally, in pricing this works as a D&C, it was priced based on comparative detailing to other box girder structures around New Zealand. In that scenario, it should have been around 50 tons. Now, with the complex FEA, we got it down to 30 tons. So that's a significant saving in cost, weight, materials for sustainability, but it also made the whole lifting operation that much easier. So, sophisticated analyses does add time, but if you can harness it and drive it for the right reasons, you can also get very good value. So we've got value here in terms of sustainability, material. We've got value in terms of cost savings, lifting, and also the architectural intent. Okay, how am I doing for time? Pretty good. So we'll move on to the laser artwork detailing. This is probably something you all come across on a more day-to-day basis. So obviously a big part of what makes the waka an interesting cultural element is the attention to detailing, particularly around the prow and the stern boards. When you look at wakas, that's where a lot of the care and the craft has been applied in that kind of detailing to show and tell the stories. So this was our primary focus here. Now, in coming up with, as you can see in this image here, we've got laser cut patterns to the board area, plus around the perimeters, and there's this tiki that sits on the face of the prow board. One of the things that was really important to the overall direction of this project was understanding the assembly and constructability of these elements, trying to integrate discrete fixings. We also had to work quite closely with the lighting integration and also structural assessment. Now, what we find with these things is not only are they subject to wind load, but where they're close to public access, so this tiki particularly, you can actually reach this when you're on the thing. So we had to allow for kids and people just giving it a yank, giving it a nudge, giving it a push. But equally, we didn't want to over amp the structural thickness just in case. Now, the problem with going too thick is it makes everything that much harder, lifting it into place, even just laser cutting it. If you go too thick, the laser cutting complexity you can get is much less. So we had to find that sweet spot. So in the early days, we developed a 3D model. One of the important things we did here is we put placeholders in for the artwork. What that allowed us to do was run the overall bridge design in parallel with the artwork design, so that we weren't rushed or forced to expedite the process. We could take our time and get it carefully crafted, knowing it would fit to these kind of placeholder templates. That was quite a key decision because it bought us time and allowed everyone a bit of freedom to work with the artworks, the laser cutting, all those complexities, and the lighting. All those elements together were quite a challenge. So you can see here one of the details. One of the things we focused on was trying to make the artwork, so the laser cutting, as simple as possible. So in practical terms, it's just a 6mm stainless steel plate. There's no welded elements to it. There's nothing other than drilled holes for fixings, and it's just a flat plate put through the CNC to be cut. So working through how that attaches to the structure without having to add kind of cleats and fixings and all those other kind of processes was quite important. So here we've got this is kind of half of a PFC, so a parallel flange channel. This runs the perimeter of the prow board and the perimeter of the stern board. What that allows is it allows us to have this central stiffening plate, which does the structural work, but then it creates this void. What that void allows us to do is when we have the laser cutting, in daytime, it creates a beautiful negative detail. And in the nighttime, it creates an area to install the lighting. You'll see that in a second. Obviously, with lighting, it has to be integrated. You have to work out where you're putting the lighting because no one wants to see that lighting other than what it displays in the end. So we don't want to see the fixtures or the fixings for the lighting. So creating this parallel flange, almost sandwich profile, we have a laser cut this side, central structural piece, and then we've got a laser cutting on the other side. This is symmetric about this central board. So that was quite important. And you can see here, the fixings are very simple. It's just, I think that's a stainless steel tech screw, isolated with a rubber washer, and all of the kind of the hard work is done by the structural steel. So there's a cleat to receive it. You know, the structural steel is pushing away to create those voids, but the laser cutting is kept as simple as possible. And you'll see that in some of David's later slides, that the laser cutting was a flat panel, and that helped everything. And keeping it at 6 mil was really important. Now, how did we receive the artwork? So we had those flat panels that we passed to the artist, and then the artist sketched for us what he wanted. Now, I've got to be honest, it was an actual sketch. So we tried to convert that to CAD, but the problem is it picks up all the nuances of actually a sketch detail. And you'll see that in the next slide. So when we actually created raw CAD from the sketches, we had all these kind of crazy little bumps and curls and gnarls. So we did have to do a sanity check and go back through the CAD and just take out some of the craziest kind of sketchy elements. You see on the right here, there's quite a few almost sawtooths. That's literally the placement of the thick black pen that was used. And as you press down, it kind of just creates local blotching, and it was picked up in the conversion. We didn't change all of that. So the final artwork is very much the raw sketch from the iwi artist. We just tuned some areas where those little nuances might have been a bit too overpowering. Once that was done, we had a CAD face that we could then put back through our 3D modeling and put them back into those placeholders. So in the meantime, the entire bridge and the piers and the foundation, they've all been designed in parallel. But knowing in advance what the placeholder, what those canvases were in terms of size, meant once they were detailed, you could fit straight in. And you can see here, this was the intention, and you'll see in some of the later ones, it's exactly what was delivered because the process was right. One of the things obviously we struggle with is, and I've talked about earlier, about wind and just that kind of people swinging on it, pushing it, feeling like they need to challenge it in the field. We've all done it. You know, you walk up to something and sometimes you'll give it a nudge, you'll give it a push just to see what it's about. So we had to make sure that this thing was robust, but we didn't want to just chuck material at it. So one of the processes we created is we put the artwork into CAD. We then developed a bespoke, I guess you would call it an application or an app, that took the CAD and changed it quickly into an FEA model. So it actually goes through the CAD and works out what is solid space, what is blank space, and builds a model. Okay, so you can see here, this is from our Monganui Gorge Bridge. That's the balustrade infill. But here's the tiki from the Waka Bridge that we used it on as well. And that then goes on for us to look specifically at the areas that might be struggling. Now, obviously, with these intricate patterns, it's normally in the regions where the pattern's reducing to such an extent that it creates like a bottleneck. So you can see here, we had some areas here, but there was a particular bottleneck through here that needed analysis. And, you know, this is pretty unusual. We've got a full FEA model of the architectural tiki just to make sure it could do its job freestanding without becoming 10 mil, 12 mil plate. You know, we could keep it at the 6 mil plate because we could prove it. You don't want to find this. You don't want to find out after the fact that 6 mil is wobbly as hell. So this is where this adds value. It allows us to edge our bets in terms of we can go thin plate, which like David will talk about later, that thin plate is easier to cut. Okay, by going as thin as possible with proven analysis, open the gateway for a nice, complex, intricate pattern that adds a lot of value. The detailing, so you can see here, so this brown kind of framing element, this is the PFC. So you can see here in the top right-hand corner, this is symmetrical, but half the PFC stands proud of this central board. So you see here the brown background, the negative detail, that's this central board. And then the framing is the PFC coming over the top with these cleats to receive the artwork. And here, what this detail is showing is we used a INEOS Eon Flex Pro flexible LED system. That allowed us to kind of go up the inside of the PFC and get this whole area lit. Now, the flexible INEOS was more about the stern, because the stern's actually a curved shape rather than the kind of the more straight shapes of the prow. But again, considering how we integrate the lighting, how we get the negative details, how we get the fixing, is really important. And that's probably one of the strongest elements of the Waka Bridge, that awareness of what we want to do architecturally, culturally, with the intent, and making sure the details are considered from an early phase so everything comes together seamlessly is quite important. Here's a version of the lighting. So we do have under handrail lighting, more of a kind of a functional lighting, and that also comes down the staircase. And then we've got the architectural lighting to the prow and the sternboard. I mean, the sternboard is massive. It's like 8 meters tall. I think it's like 1,500 mil deep. It's huge. This thing probably doesn't give it the scale of its actual outcome. But you can see that lighting has done its job. It lights all the way through that kind of negative space. And we had quite a few mock-ups in the office, quite a few days where we had to black out all the windows and get the lighting to see if this would do the job. And obviously it did. So that's a great outcome. Also, a really important consideration was around parts and assembly. Like I say, this overall sternboard is huge. So it wouldn't be practical to have this as one laser cut element. We had to work through, well, what are the stainless steel sheets available to us? So this is probably an important lesson to learn when you're doing detailing with this. Start from what are your sheet sizes? What can practically be sourced and supplied within New Zealand? And then work backwards, because that will define your assembly segments. Okay, so you can see here, even on our drawings, we explain what parts and what sheets we're expecting these to be cut from. So you can see this panel number 2 was cut from a 3 by 1.5 panel, whereas number 3 was from a 2.4 by 1.2. So having awareness of available sheet sizes and then working through your assembly is really important. We also played a little bit with the sections. Rather than having a straight cut, we created a bit of a fun shape with the cutting itself, and that added quite a lot of value. Rather than trying to hide the cut, which was almost impossible without adding complexity, we tried to create a bit of fun with it. So in terms of the panels, you've got these cut edge, and we've also got these holes. These holes are your fixing points onto those cleats I showed you earlier. So overall, this was quite a fundamental drawing. This is the stern plate detailing drawing that shows the plate assemblies and shows how they attach. And obviously the DXF file, so the raw CAD file, was then sent to the fabrication team so they can plug it straight into the CNC machine. So a very kind of smooth, quite easy process, because we all thought about the process in advance and decided what we wanted to get from the process. And there's the outcome. I mean, this sternboard is a thing of beauty. But you can see here the shapes of those components as they come together. We're not trying to hide it. We're trying to make fun from those elements. And you can see that the fixings, they're pretty discreet. It's a stainless steel mech fixing on a stainless steel plate. You have to look hard to find it. It's one of the things, once you find them, you can't not find them, but typically people don't see them. But we find the assembly cuts to be quite playful and actually a really good outcome. And you can see here, there's the tiki sat on the front of the stern. And again, that's been sized, so you can give that thing a grab and yank. And well, I wouldn't recommend that, but you can, because it's been designed for that. It's been designed for wind. We know it can do its job. Obviously, it's done well at the SCNZ Awards. Seamless integration of art, culture, and engineering, which is basically the purpose of today's meeting. The artistic intent embedded in every structural decision. And that's really the key message here, that we haven't created a bridge and then clad it to look like a waka. Everything has been woven together into one outcome. And I think if you can get that in your projects, the outcomes speak for themselves. Okay, that's all I'm going to talk about today. I'm happy to take questions as we come on to the end of the session. I'm going to hand over to David now, who's going to talk through fabrication and erection.
Yep, thanks very much for that, Dan. Dan is to his credit, he's very in tune with the requirements of the fabricator, and he's had a bit of a relationship with Eastbridge, so he's quite good at knowing what does and doesn't work from a fabrication point of view, which did make this project a lot easier. I think one thing that I would say that facilitated this project is we had a very tight collaboration between Dan, the designer, Eastbridge, the fabricator, and another chap, Andrew Fletcher, who is our detailer. So slightly unique to this project, Eastbridge engaged both Dan and the detailer directly. So we had a very small circular relationship right from the inception of this project. So the fabricator was heavily involved. And I think it shouldn't be underestimated the benefits that added to the project. Part of that was, traditionally the architect or designer would produce a full set of detailed drawings and present that in a 2D format. That would get passed down the chain to the fabricator. We would then engage a detailer, and basically they would start from scratch and redraw the whole structure in a totally different package. However, our detailer, Andrew Fletcher, and Dan collaborated very tightly on this project and actually did that function in parallel. So Dan didn't spend all the time and effort producing 2D drawings. Our detailer actually facilitated with that, and we cut a lot of time and effort out of the process, and the benefits of that are quite apparent. And I think the main benefit, which you'll see on the next slide, thanks Dan, is that the renderings that were produced by that collaboration at the start very much have borne out in the end product. I mean, what Dan conveyed to the stakeholders is what was delivered in very tightly alignment. I think that collaboration shouldn't be underestimated, and it's quite worthwhile going forward. Like in a usual construction arrangement, there might be 3 or 4 layers of separation between the architects or the designers and the detailer, but in this case there's a very tight relationship, which I think the images here show how easy it was for us to produce what Dan conceived of at the start of the project through that collaboration. Next slide, please. Because the various elements of the works all had some quite unique geometry, we did actually rely heavily on having a very high quality set of steelwork fabrication drawings, which are indicative here. Bearing in mind that all steel starts as flat plates, there was a lot of work involved in that geometry and taking that flat plates and turning them into flat patterns that we could manipulate. So we needed to have the good information to start with to start off on the right foot. And next slide. Thanks, Dan. The next part of the puzzle for us was we had a very good set of drawings to start with, but actually we needed a very good and skilled crew of fabricators to, produce some of this complex geometry. So it took a lot of skilled fabricators and a very methodical approach to execute this. This image here, you can see the hull itself. Geometrically, it's reasonably simple. It's only a constant radius curve, that hull, so it's not overly complicated. So that was manageable. But if you look at the next slide, thanks, Dan. You'll see that the prow and the stern elements, they take another step up in terms of the complexity. Another definitely higher notch of complexity. Both the prow and the stern, in this image you can see the stern, those skin plates are structural elements, as is the hull, and they're about 10 millimeters thick, all those steel plates. So those plates aren't just 2-dimensional curves, they're actually 3-dimensional compound curves, which are certainly quite challenging to manage and fabricate. But again, that just came down to a methodical approach from the guys, and some very highly skilled guys doing that work as well. So we really relied on the experience of the fabricators to produce this geometry. Next slide, thanks. One of the things that cropped up quite early in the process was how we were going to treat the welds on the outside of the hull. So it would be very easy, and I think we all anticipated that we would be grinding all the welds flush, as would probably be expected, but we actually took a different stance on this. Once we started welding, we consciously decided or suggested that we'd leave them proud, and that left photo is actually a mock-up we did. We welded a section of the hull, sent that through to Dan to have a look at and to consider, and then we just decided we'd actually leave the welds proud. And the main reason for that was actually aesthetic considerations, which might sound counterintuitive, but the real risk we had with such a long flat structure like the hull on you can see on the right is we get this like cupping or oil canning effect where when you're welding down those seams, the heat sort of bows the plate inwards. So if we had ground those welds flush, we would have this series of cups along the hull, which we thought would probably be not very desirable. So we ended up leaving those proud, and I think that has made a big difference. It really masks the sort of oil canning cupping effect. So, and the justification for leaving those welds is also we wanted to show or display some of the workmanship of the fabricators, you know, have that visible so people could appreciate that it was, you know, humans that built this. I mean, and it's easy to justify because if you look at a traditional waka, you can clearly see the craftsmanship and the workmanship and the evidence of it on a traditional waka. So we sort of just mimic that and honour that by leaving some of this workmanship visible on the project. Next one, thanks, Dan. Yeah, so that one, the spiral staircase also presented quite a geometrically challenging project, and this photo shows it as one big structure, but actually it is 6 or 7 small substructures, and it was designed as substructures, so it was easy to transport, and the installation logistics would be a lot easier. So we initially thought we would build it in its 6 or 7 sub-elements as you would normally. But with the complex geometry, we decided that the amount of checks and balances that would be needed to build a substructure in its sub-elements, you know, would be quite a time-consuming process and quite a risky process. So we actually ultimately decided we would build the whole staircase in its full entirety in the workshop, which actually de-risked the project quite a lot and was a lot more straightforward in terms of checks and balances. So we did build it in full, which is quite tall. It's probably not visible in the photo, but I think it's about 7 or 8 meters tall, that thing, when it's finished. And you can see that basically there is no wasted steel on the staircase as well. So as one of Dan's mandate was to design a very efficient structure, and it's reflected in the staircase as well, because there's no substructure to the stairs. Those stairs you can see on the left are the structure. So everything is functional. There's no wasted material. That is a particularly highly efficient structure. Which is challenging in itself, but the team did a good job there. Next one, thanks, Dan. Yeah, so not too much to see here, but that's the approach ramp on the Kaitia Hill side of the structure. Also designed as a sub-element that was easy to fabricate, install, transport. Moving on, thanks, Dan. Similar again, it's just a installation. You can see quite a straightforward, simple bearing arrangement on this, which was useful. You can see the prow just in the background there, ready to be installed. Moving along, thanks, Dan. So one of the key things for the ease of installation of this was splitting the hull into 3 substructures. First one being the main hull, as can be seen here, as well as the prow and stern sections separately. So splitting the 3 vessels was primarily governed by transportation requirements, particularly with the stern being such a tall element. It actually became very relevant for us because we started the project before Cyclone Gabrielle, and part way through, Cyclone Gabrielle affected us quite badly, and that affected the road conditions between Napier and Gisborne. So fortunately, we had designed it in such a manner that it was easy to transport, because the transportation logistics became substantially more difficult. Next slide, thanks, Dan. Yeah, so this one is just showing the main hull section, which was and the splits on those are very convenient. You can see once the central section here lands on the two piers, and that load itself is a very uniformly distributed weight. So the lifting and rigging arrangements, as you can see here, are very simple and very easy to manage. So that was very convenient. Next, thanks, Dan. Yeah, so this again was one of the main reasons we split the structure into three elements, because the stern section here, as you can see, is quite substantially large, and would have been virtually impossible to transport in another state. There were considerations about splitting this into sections again and site welding it, but eventually we just settled on raking it over like that and transporting it in one piece. So I think for us, it would have been very easy for Dan to determine that the easiest path forward was to site weld these three portions on site, which, I mean, it is an easy decision to make because there is no design input to having a welded connection, but there was a lot of time and effort put into the bolted connection, which was extremely advantageous for us for a number of reasons. You can see here, the connection was designed in such a way that it's virtually indistinguishable from outside the vessel, which I think is the key outcome. But there was a lot of thought put into how that connection came to pass. So to connect it, we did require having holes in the structural steel floor element. You can see the two holes on the left of the image here to provide us access inside. The prow and the stern sections actually had no access internal at all. So those sections were produced with a type of nut welded to the inside face. So we didn't need the access. And then on the night of installation, it was a very, very quick and easy process to bolt that up. I mean, literally 2 to 3 hours, those connections are made on site each night, which alleviated a lot of the site constraints. I mean, it meant we didn't have to have any temporary works for supporting those prow and stern sections while they may have been welded together. Took out all the site welding and all the risks associated with that. So the design of that was exceptionally good and exceptionally functional and straightforward. Next slide, thanks, Dan. I think you skipped one there. Yeah, that's just a bit of a detail on the inside, which doesn't show much, but it does show some of the alignment dowels we used to facilitate joining the two halves on site. But yeah, good solution and pretty well thought out, thanks. Next slide. Yeah, so that's just coming closer to the finish line. Obviously, the staircase did come up in a lot of sub-assemblies, which took 3 or 4 or 5 days to assemble on site, but that went quite smoothly. Next slide, thanks, Dan. Yeah, just a bit of a detail of how some of those internal connections were made. So all the shrouding system fixings were virtually indistinguishable from the outside. We did have splice plates on the inside to connect everything. So there's a lot of thought put into hiding the fixings and making the external structure as clean as possible. Next slide, thanks. Yeah, that's just another example of the elements going together. So I think Dan might correct me on this, but there's some existing structures in and around that area which were made from Corten weathering steel. So that structure you can see on the left there is a weathering steel structure. And I believe that we colour matched the hull. And I think Dan went to site and held some swatches up against that to actually select the shade of paint we've got on the structure. So the structure is painted steel rather than weathering steel. And there is a specific reason for that. I think it's because it's over the road and there was
No,
consideration.
We were too coastal. So if you have a weathering steel in a coastal environment, it degrades too quickly. It doesn't create that patina. So we would have had to go for marine grade weathering steel, which would have just blown the budget. Now, it's okay for the sculptural works because they're non-load bearing, but as soon as we went to something structural, we couldn't risk the long-term durability issues. So that's what drove the decision not to go with weathering steel, but instead match.
Yep, it makes perfect sense actually, doesn't it? Because one's structural, one's non-structural. Yep, next slide, thanks. There's just a few more examples of the modular nature of everything and the site assembly process. I think us building the staircase and the workshop in full made the site installation period substantially shorter. It's definitely advantageous to have it built in the workshop. There were a few issues which the trial assembly in the workshop did raise, which just reinforced the reason for doing the full assembly in the workshop, because we were able to troubleshoot a few issues on site. And the only troubleshooting was related to the circular shroud plates and managing their alignment on site. So we added some extra features to make sure they were aligned and had clean, tidy transitions between the circular shroud. This one must be near complete. And I think in this photo, what's probably interesting to note is you virtually cannot tell where the spliced connection is. In this photo, actually, the spliced connection is where Dan's cursor is now, one bay to the right of the pier. I mean, unless someone pointed it out to you, I don't think anyone would actually ever see that spliced connection. And I think that's a credit to the design and the execution that we were able to put that structure together and not have any distinguishable assembly marks. And I think Dan has already talked about it, but I think it should be reiterated how easy and cost effective this artwork's implementation became on the project. So this project was constrained commercially, and so there was a lot of conscious decisions around how to do things cost effectively. And I think the inclusion of the stainless steel artwork, which was a secondary budgeting issue, came through, it was remarkably cost effective. The reason this photo is included is you can see on the left, this panel on the left is exactly how it's come off the laser cutter's bed. Literally, it came straight off the laser cutter's bed, no human involvement. That went straight to site. All that we did was peel off the adhesive protective sticker and bolt it straight on. It was as efficient as, you couldn't have done it more efficiently. And I think people are sometimes swayed away from stainless steel because of the raw material costs, but yes, the raw material costs might be 5 or 6 times the cost of a carbon steel plate, but if you'd had to take the same equivalent carbon steel plate and put it through a painting process and all the handling and extra requirements to paint steel, you'd quickly erode those gains that you'd made by using stainless steel. So stainless steel at face value is quite expensive, but ultimately on this project we would utilize it in such a way that it was highly efficient and achieve the outcome at a very low cost. So I think, that was definitely a good addition. And essentially, that is the end product. I think this was a few days before it was open to the public, so that was in its final state. And and I can't say much other than just a pretty good outcome. Fabrication team, the design team, collaboration between Dan and our detailer and our team. I mean, speaks for itself, I think.
Oh, and I'd like to thank both the Ds. I just realised we're 3 Ds today: Darren, Dan, and David. Sounds like a 1970s pop group. But look, what a fantastic project, and we've got a couple of questions just to close up. So the first question was, hindsight being a great thing, what would you have done differently in the project? We'll start with Dan, I suppose.
What would we have done differently? It's difficult on this one because I don't think we can overemphasize just how bespoke every element was. So I think a lot of the lessons have been much more positive because we had to put our brains to every challenge. Most things were solved before they became an issue. I can't really recall any real issues on the site. I guess one of the hardest things was aligning the spiral staircase skims. That was a challenge. I don't know how we would do that any differently. It was just a case of skill and care by the installers and a dedication to their craft. But I can't, I mean, it might be a good question for David. Anything we could have done better for you guys when actually trying to put it all together?
No, I think the early collaboration meant that we'd resolved most of the issues before we got into it. So I don't think, I can't personally think of anything that we could have done differently or better. I mean, there's small things here and there, but nothing of significance. Yeah.
Cool. Okay, I've got another question here. What is the design What is the design criteria adopted for bridge design, IL and DL? So I don't know what those stand for. I'm sorry.
I can't recall off the top of my head. This would probably be an IL2 because it's a footbridge. So that's an importance level. So just for those who don't know, importance level will define the size of seismic event, the size of flooding and things. Most of those things didn't govern this design. This design was governed by dead plus live load. And we also had to design, so the pier to the right there was designed for truck impact. Because we're so close to the road, it was either a case of putting massive great concrete barriers or offset everything and ruin the footprint, or just design for it. So the pier here, the staircase, they've been designed for truck impact. So the importance level, it is a 2, but it didn't really drive too many decisions. Maybe a little bit of seismic, but not many of the governing criteria. What was the other question? Importance level and
DL.
Design basis, was that the other one? It's designed to the NZTA bridge manual, which is a guideline for designing bridges in New Zealand.
Well, thank you. Second question, I think I've got a couple people their hands up as well. But the second question we've got, or third question, is what compromises did you make in terms of moving from design to fabrication to ensure buildability?
I don't think there were any compromises.
No, it doesn't seem to be.
There was
I guess that goes
everything
hand in hand.
Everything that Dan wanted, he got.
Yeah. Well, I think it goes hand in hand with what David's saying. It wasn't. I didn't design it and give it to the fabricators. It was so interwoven because ultimately I was engaged by the fabricators. And we're probably underplaying Andrew's involvement, like Andrew, the detailer. So I originally did a concept in Trimble SketchUp. Now the detailing is done in Trimble Tekla. The two pieces of software talk really well together. So we created the bridge in SketchUp, and then every now and again I would hand over an element and say, right, this is ready now to detail. Andrew would then detail it in Tekla, and we would bring that back into our model to replace the element that was originally in that model. So both models basically trended towards one another, so that in the end there was only one model left. So it was ultimately, there was the steel model for the steel combined with some of the concrete stuff that was done offline that remained within our kind of drawing packages. So so I guess, and I think David touched on that throughout his session, was that interwoven collaboration meant it wasn't stage 1, stage 2. It was just pure delivery all the way through.
Yeah, I don't think there was any compromises as such. Probably the only thing that may not have come to fruition exactly as intended is the prow and the stern are a compound curved. And if you look hard enough at what we actually outputted, you would see we've outputted it in a slightly faceted sort of nature where it's not a true nice compound curve, but I think that just
that's just the perfectionist in you there, isn't it?
Yeah, but it just adds sort of looks more of a handcrafted structure rather than a nice smooth polished fiberglass boat hull. You can see the craftsmanship in the prow and the stern being not quite perfect.
And I think that's quite important as well, isn't it? That, what David's picking up there is something none of you will see, but it's that attention to detail that every team had. Every team approached this as a kind of almost a once in a lifetime ability to demonstrate their craft. Okay, if you're not going to get out of bed and do your best work for something like this, when are you? And I think everyone came to the table wanting to do their best, and this is what you get.
Cool. No, thank you. We got, how is the rainfall water handled?
I mean, so you can very discreet here. You see these little notches? These are little downpipes that are in the deck. So the deck has a crossfall and a little gully channel, and it picks up, and the rain just pours out of these little holes that you probably didn't even notice till my cursor went there. So it's all thought through. The only thing we didn't allow for is there's a bit of debris that comes from this tree that can block those channels at certain times of the year. But ultimately it does pass through. It's no different to normal kind of footway drainage where tree debris can block drainage things. The intention was to kind of prune this tree, but we later found it was a protected tree. So hence why this huge tree is still there. It does block some of the views, but that is part of it. But yeah, there's drainage implemented in. And again, this is everything. It's making sure that all those functional elements are carefully considered so they don't ruin the overall outcome.
Cool. We also asked, someone asked, pretty got time for 2 more questions. Is the artwork on the whole painted on?
Yes, I believe so. So actually, that came as a secondary thing after Dan and Eastbridge's involvement exited. But yeah, I believe the artwork on the hull was, I think some masks were created, and then the masks were applied as a sticker, and then the paint was painted on literally using those masks, which looks pretty fantastic.
Amazing, doesn't it?
Fantastic, right? Last question. Have you performed any buckling analysis on the shell?
Yeah, of course we did. I don't know what else to say. Yes.
Yeah, definitely.
That was the whole point of the FEA, was literally understanding the behavior of the hull as a structural element and the complexity and level we had to go to on that. I mean, it was all designed to the Eurocode because there's nothing in New Zealand to that level. So we had to kind of build it from scratch in an FEA model and follow European guidance on how to assess the skin and work out where and where not to apply stiffeners to make sure that the skin itself didn't buckle. Okay,
well, we have got one last question, and why a steel bridge? Well, we won't complain about that, of course. Wouldn't a timber bridge be more appropriate for this Waka bridge?
Oh, not. Yeah, Dan can answer that, but I think you'd struggle to get the structural integrity to span across the road as you have. But Dan will know.
Yeah, it's. Where would you start? For instance, bear in mind we were tight on program, we were tight on budget, so we had to start from something that we could prove. So obviously, you can prove a steel box head system. To build it as a boat would be a big maintenance issue. I think it would come down to more about maintenance and trying to make sure there was. I mean, the hull, if you got it wrong, would collect all the water in the base of it. Then you would have to try and seal it, and you would never. It's not like a weld where it's perfectly sealed. Trying to seal that timber Waka, it's about long-term durability and maintenance for council. It's ultimately what that came down to.
Yeah. Cool. Hey, look, everyone, I'm conscious we need to run exactly to